heat waves, drought, tornadoes, hurricanes, floods, blizzards, bitter cold. Extreme weather has an incredible impact on people across the globe. On Mount Washington, our scientists brave some of the worst weather on the planet to improve our understanding of our warming world. All right, good evening, everyone, and welcome to Mount Washington Observatory's Science in the Mountains program. My name is Brian Fitzgerald. I'm the Director of Science and Education here at Mount Washington Observatory. Joining me live this evening from the summit of Mount Washington, as you can see, Nicole Tallman, Weather Observer and Education Specialist for Mount Washington Observatory. We also have John Jensenius joining us. John Jensenius is a retired National Weather Service meteorologist. He also serves on the National Lightning Safety Council, and he is a lightning safety specialist. So we'll be hearing from both Nicole and John this evening. Thanks again for joining us tonight. So far, we're seeing quite a few of you joining in. Excited to have you with us. For those of you who are not familiar with Mount Washington Observatory, we are a private, nonprofit, member-supported institution. Our mission is to advance the understanding of the forces that create Earth's weather and climate. The way we do that, a few different ways. We maintain a year-round, 24/7, 365 weather station on top of Mount Washington where we conduct weather observations and daily forecasting. We also conduct innovative educational programs and research and product testing projects. So a lot going on at all times. Again, we appreciate you joining us tonight. For those of you joining us on Zoom who need a quick refresher on how to navigate Zoom, a couple different features to take advantage of tonight, including the chat feature on your screens. So if you hover down to the lower right, the lower bottom of your Zoom screen, you'll see a feature for chat. Feel free to give a shout out from where you're joining us from tonight. A couple weeks ago, we had folks from all over the US and beyond, so we'd love to see who is joining us tonight. In addition to that, there's going to be a Q&A section later on in the program. So as you have questions, we'd love for you to ask those questions via the Q&A button, which you can find again at the lower toolbar on your screen in your Zoom screen there. So as you're thinking of questions you'd like to ask Nicole and John throughout the program this evening, please send them there and we'll make sure there's plenty of time for both of them to try and answer your questions tonight. We're seeing lots of folks joining from all over, including all right, my hometown, North Conway, New Hampshire. Glad to see that represented as well. But from further afield, I think, Oakland, California. Amy Shea joining us from out in the Bay Area. Great to have you with us tonight. Shrewsbury, Vermont. We have Massachusetts, well represented. Tallahassee, Florida. Timothy Cross, thanks for joining. Oh boy, all over the place. Ipswich, I know some people from Ipswich as well. Excellent. So glad to have so many different regions represented. I'm sure we've all had some different experiences with the weather today. Sorry we didn't have any thunderstorms for tonight's program, but that's okay. That allows us hopefully to do our program without any hitches. So we'll get right to that. So as we're moving along here, and before we hand it off to Nicole, we have some questions for all of you who are joining us tonight. And I'm gonna launch a quick poll here before we hand it off to Nicole. And you're going to see 4 different questions. If you're joining us on Zoom tonight, by all means, please participate. If you're joining us on Facebook Live, apologies that you're not able to join in on the poll tonight. But if you want to join us for some more interaction and upcoming programs, we'd encourage you to register for the Zoom programs at mountwashington.org/SITM. So we see some questions starting to be answered right now, starting to see some responses that I'll share in just about another 30 seconds or so. We're seeing if any one of you, it sounds like we have quite a few people who attended our first program, so welcome back. Always curious to see who our supporters are out there, who are our members supporting Mount Washington Observatory. And then we have a couple trivia questions that we're going to get to tonight. What type of thunderstorm produces the most tornadoes in the United States? And then which US state on average sees the most lightning strikes each year? So we have a number of options here for you, and we'll end this in just a second here, and we'll see what our results are. All right, let's see. How did we do? Did we attend the first program? About 50-50. Well, welcome everyone who's new for this program, and welcome back everyone who joined us for our first virtual Science in the Mountains program. Hope to see all of you for our upcoming programs as well. Quite a few members, 35%, not so bad. 40 out of the 113 of you who responded. If you're not already a member at the observatory, well, there's a great opportunity following this program to go to mountwashington.org to sign up and support the observatory. We certainly appreciate it. And it looks like we already have 16 of you who said, you know what, they're going to do it after this program. So let's not disappoint. And then, all right, what type of thunderstorm produces the most tornadoes in the United States? Ooh, quite a few of you said Supercell. A couple said derecho. Some people think Squall Line, some single cell. Nicole's going to give us a little more information on that in just a bit. And then this is a tough one too. Which US state on average sees the most lightning strikes in the US? A few of you said New Hampshire, Texas, quite a few, California, maybe not so much, and then Florida coming in about 50%. All right, we'll see how all of you did. So we will stop right there and tell you what, enough from me. Let's hear from Nicole. Nicole, take it over. Let's hear about some thunderstorms and how they develop.
All right. So thank you for joining tonight. I'm going to be, the first part of this talk, I'm going to be talking about thunderstorms. And I personally am very excited to be talking about thunderstorms because that is why I got into meteorology. Those of you that know me that are on this chat, I have seen a few of you, know that I absolutely love thunderstorms, and I am always glued to the window watching them happen, and that it still stands true today. It stood true when I was 7 or 8 years old. So I am super passionate about this topic, and hopefully I get to teach you guys a little bit about why I'm passionate about these storms. So jumping right into it, what is a thunderstorm? We all know that it's thunder and lightning and rain. The skies get dark and there might be a clap of thunder or a rumble of thunder. But up here on Mount Washington, we do have a specific definition that we go by when we do start to see storms develop. So this is going to be a local storm, meaning it's a little bit smaller scale. It's produced from a cumulonimbus cloud, which is actually the cloud featured behind me. I know it is a little challenging to see. I will make it full screen. So a local storm produced out of a cumulonimbus cloud associated with lightning and or thunder. So those are going to be our defining characteristics of what a thunderstorm is. Typically, we will see these storms start to develop in the spring and summer months in the afternoon hours. And now that's important. We will get into our next slide talking about why the afternoon hours. So for a thunderstorm to happen, you need there to be 3 key ingredients. The first one being lift. So we need air parcels to rise in the atmosphere. And there are 3 main ways that we start to see those air parcels lift into the sky. The first being thermal lifting, which is what I referenced in the previous slide, that towards the afternoon hours of spring and summer months, we might start to see warm air at the surface that has been warmed by maybe the ground, the concrete, anything that's absorbing heat. All of that's going to warm up, and those air parcels are going to start to rise in the sky. So if you've ever been on a top bunk or went up into the attic, you know that hot air rises. So that's going to be a key ingredient to know for thunderstorms. So this thermal lifting is just our first type. We also have what's called orographic lifting, which is going to be something that Mount Washington is familiar with. So this is any kind of geologic feature like a mountain that maybe causes air to rise above it. So you're going to see these arrows going up and above a mountain range. Now, Mount Washington here, we like to joke that sometimes it'll make or break those thunderstorms. So we definitely do have the lift of our mountain range to cause that air to go up into the sky. The last one is going to be frontal lifting. So when you have 2 bodies of air masses coming towards each other, one of those is going to have to give and go above the other. So that is the 3rd type of lift. All of these are going to force air parcels up higher into the sky. So that's our first ingredient. Our next ingredient is going to be what's called instability. So to be an unstable piece of air, you have to be given a nudge upward and continue to rise. So not only do we want that air to start to rise, we want it to continue to rise, to form into these storms. We don't just want it to come up and over Mount Washington and then back down to the ground. So unstable air masses are going to be our second ingredient. And our third is moisture. If we didn't have moisture in the air, all of this lifting wouldn't do much. So we need moisture to be evaporated into our air. We, in the United States, we get our moisture from the oceans, and more specifically, warm ocean currents or warm ocean waters. So areas like the Gulf of Mexico and for the East Coast, they're going to have warmer oceans, and the air is going to be able to evaporate more of that moisture. So that's why areas to the East Coast are going to see a little bit more thunderstorms than areas to the West Coast, one of the main reasons. So this picture here is showing our warm, moist air at the surface is going to start to lift up into the sky to where it's going to be much cooler and drier. Cold air can't hold on to as much moisture. So as it goes up and then it comes down, it's going to form this convection cell. So that's another key word here, is a convection cell. That is going to be the rising and falling of warm air and cold air. So taking a look at this next slide, what you're going to see is developing. Now where I want you to focus when this video does play is right up here in the top part of that thunderstorm. I want you to watch and see if you could see that rising air and notice a little bit about how this thunderstorm is forming and what it looks like. So I'll make this full screen and I'll play it for you. Reminder, just look at that top part of that thunderstorm. So this is one of those cumulonimbus clouds that I was talking about. And as you can see, we can actually see the air starting to rise up right in the center of that storm. You can see it spreading out on the top and even bubbling over on the top right there. So that is what's called the Anvil top and the overshooting top of a thunderstorm. So again, this video was taken by myself up here on Mount Washington. So we do see some pretty awesome thunderstorms up here on the mountain. All right. So how does it become that beautiful of a storm? So it starts off with just those white puffy clouds that you guys see outside on a fair weather day. We call them fair weather cumulus clouds. So the cumulus clouds are going to be the ones that look like a cotton ball. As they start to have that instability, they're going to rise up and keep rising. And they're going to form a cloud that looks like this right over here. Now this was also taken up here on Mount Washington. And as a weather observer, when I see this cloud, I'm going to report it differently. Why? Because this cloud is showing that there is an updraft starting to form, which means that there is rising air in that center column of that cloud. So we call this one a TCU, or a towering cumulus cloud. And when we start to see these TCUs form, we know that there is an ingredient there that can lead to thunderstorms. We know that there's starting to be some lift, starting to be some instability. So that is a little bit concerning to see out in the sky. We know that maybe a thunderstorm could be forming. That updraft is starting to occur. It could form into something bigger. So the next step would be to continue growing and to continue rising up and forming a cumulonimbus cloud. So we're going to see in this picture here that there are some red arrows kind of going up. That is the warm updraft. So that's that rising hot air. Think about that attic or that top bunk. Rising hot air is going to keep pulling things up, pulling the cloud up, and it's going to hit kind of a lid where air can't rise anymore. It is going to start to get colder in that section of the atmosphere, so the air is not going to want to rise up. That is going to be called the tropopause. So we live in the area of the atmosphere called the troposphere, and at the top layer of that is called the tropopause. So as this air is rising and rising and rising, it's going to hit an area where it doesn't want to rise anymore, and it's going to spread out. That is called the anvil top to the thunderstorm. So you can see that it kind of makes an anvil shape. When it hits this top area, it's going to get colder. High in the atmosphere is actually colder in temperature. So it's going to get colder as it rises and then fall down with these blue arrows as a cool downdraft. So we have our updraft, our downdraft, our tropopause, and our anvil top. And sometimes when that updraft is strong enough, it is going to pierce through that little lid that we just talked about. So it pierces through as an overshooting top. And you saw that on the previous video. You can also see it on this picture that I'll show you. That is almost a picture-perfect representation of a cumulonimbus cloud. Again, I took this picture same day as that video that I just showed you here on Mount Washington. And it's pretty impressive to look at these side by side and actually get to see that anatomy of a thunderstorm and understand what's going on inside of this picture. So thunderstorms can form some awesome cloud types, and personally that's one of my favorite parts about watching thunderstorms is seeing what type of awesome clouds are going to come out of this. So this is called a shelf cloud, and it is going to be that the outer reaching band of clouds that kind of surrounds the precipitation underneath it. So I'll make this full screen so that you can actually see that overreaching cloud. Now this cloud was taken from a severe thunderstorm warning down in Myrtle Beach when I was much younger. Another very cool cloud is called the roll cloud. So sometimes thunderstorms will push out that cool air in a gust front. And as that gust front goes in front of the thunderstorm, it's going to cause this rolling sensation. So it's going to have these clouds kind of rolling ahead of the thunderstorm. Now that means that it had a gust front come out of it and that the storm is going to be approaching you. Now these are called mammatus clouds. They are my favorite cloud. They indicate that you are on the backside of a thunderstorm. And when I said that that air was rising because it's super hot and then it overstretches, well, it doesn't have anything keeping it up in the air anymore. So when it goes out into those Anvil sides, it's going to start to sink down these little pockets. And those pockets are called mammatus clouds, and they look like little golf balls falling out of the sky. I personally think they're very cool, very fascinating, and they're associated with my favorite weather of thunderstorms. So these are my favorite clouds to see. We also see the anvil as seen from above. So you can actually see that physical shape of an anvil and just notice how big this cloud is compared to the other clouds around it. Thunderstorms can be massive and can be so impressive. And I think that's one of the reasons why I like them so much. So not every thunderstorm is going to be the same. There are many different types of thunderstorms. They are not all going to have the same hazards, and they're not going to all be the same size or shape. So the way that you are going to read these are all radar images. And for anybody that's unfamiliar with how to read a radar image, it is important to know for these next slides. So whenever you see green, light green, it's going to be lighter rain. And the more intense the color, so the darker the green, the yellow, the red, the pinks, those are going to be the more intense the precipitation is in those sections. So our first type of thunderstorm is a single cell and a multi-cell thunderstorm. Now these are actually the ones that we had today surrounding Mount Washington throughout the afternoon. So a very typical situation occurred where we got daytime heating and they popped up. They are little pop-up storms, you may have heard. So these are going to be your weaker version of thunderstorms. That does not mean that they are not dangerous. They all will pose their own forms of hazards. So these are going to be weaker. They last a little bit shorter, so a half hour to maybe an hour long. And a multi-cell is just going to be a cluster of these single cell pop-up thunderstorms. Maybe they formed on one of those gust fronts that I talked about earlier, where one thunderstorm maybe died and sent out a gust front, and then other ones kind of fed off of that lift, as we talked about earlier. So typical picture of a pop-up thunderstorm. Again, if you are tuning in from New England, you are probably very familiar with these types of thunderstorms. Next is going to be a squall line. I know this picture is hard to see, so I'll make it full screen. So a squall line is going to be more of a line of thunderstorms. These are going to show up on the radar as a very thin red line. Now that is showing intense precipitation in, again, a straight line. So these are most of the time associated with squalls of winds, which are generally around winds 20 to 25 miles an hour and very gusty. These squall line thunderstorms are going to be moving much quicker than a pop-up storm. And they are going to be hundreds of miles long. So they can actually span multiple states long and be pushing their way through. And they aren't very wide, so they normally are over pretty quickly, but they do again pose their own type of hazard. Next we have supercells, which are going to be those textbook picture perfect, very intense, dangerous, special type of single cell thunderstorm. So as you can see the picture behind me, if you've ever seen a picture of a really crazy thunderstorm, you're most likely looking at a supercell here. So this here, they are very dangerous, and one of those hazards that supercells form would be tornadoes. So the majority of tornadoes formed in the United States are going to be from supercell thunderstorms. And I'll explain a little bit about why later when we get into hazards. More rare forms of thunderstorms, there's going to be what's called a mesoscale convective system, so an MCS, and that's going to be this one on this side of your screen. They are going to be kind of a cluster of thunderstorms that work together as a system. So that can be a cluster of, let's say, squall lines, or a cluster of just very intense pop-up thunderstorms. But as long as they are working together as a system, they can be classified as a mesoscale convective system. They are very, very large, and they can present themselves kind of as a circular thunderstorm like this one, or lines of storms, as if it was a system of squall lines. They are very long lasting and can do a lot of damage. Now, the other more rare form of thunderstorms, actually, we had one yesterday push its way through, I believe it was North or South Dakota through Ohio. So this is called a derecho. And a derecho is going to be a very large storm that has winds gusting to 58 miles an hour for the majority of the storm. And it must have a path of destruction of 240 miles or more. So it is a massive storm and a massive area of destruction. A lot of times derechos have straight line winds that get mistaken for, let's say, a tornado. They do form a lot of damage. Actually, the word derecho in Spanish, I believe, means straight. You have straight line winds coming out of these that knock over semi trucks and knock over trees and can be very, very damaging. But they do get mistook for tornadoes a lot. So this here is a tweet that came out yesterday from the National Weather Service about the derecho that occurred yesterday. And you can see here, this is going to be South Dakota, and it shows the path of destruction all the way out to Ohio, which is 770 miles of destruction. So these are very, very long lasting and huge storms that again have super, super strong winds. They must have winds gusting over 58. Well, this storm, the strongest one that I've seen, is 112 miles an hour. So that is a super, super strong storm that would actually pass through yesterday. So perfect example, perfect timing. All right, so I mentioned that that was a tweet from the Storm Prediction Center in my previous slide. Now, who is the Storm Prediction Center? They are a branch of the National Weather Service and a branch of NOAA, and they will have this information on where they believe severe weather is going to be occurring throughout the day. So this picture here was actually earlier yesterday before the derecho occurred. So we see that there was some marginal risk, slight risk, enhanced, and moderate. I'll make this full screen so it's a little bit easier to see. So they're going to put out these risks, and then the National Weather Service themselves are going to put out watches and warnings. And I thought it was very important for me to go through the difference between a watch and a warning. So the way that I remember it is a watch would be something like watch out. Just look out for it, okay? It is favorable that conditions, favorable conditions for that event to occur. So maybe if it's a thunderstorm watch, you're going to have an unstable air mass, or maybe you have a lot of lift occurring, you have a lot of daytime heating, so there's a chance of that to happen. There's favorable conditions for it. So it doesn't mean that it's necessarily happening, it means that it possibly can. Warning, in my mind, sirens are going off. So if you get, let's say, a tornado warning or a severe thunderstorm warning, that means that you need to act now and that there is a serious threat. So the event is already happening and you are in the path that it is coming in. So we have our watch and our warning. Now there's also going to be severe thunderstorm warning, so that another threshold to cross. And in order to be classified as a severe thunderstorm, you need to be either having hail of 1 inch or more, or you need to have winds gusting to 58 miles an hour or more. So that is going to be your severe thunderstorm warning, as opposed to just a thunderstorm watch or warning. All right, now into our hazards of thunderstorms. A little bit about where we're going into this talk is safety. So there are many hazards that come with thunderstorms. As I have mentioned, even though there may be smaller, weaker thunderstorms, they're all going to be hazardous. So we have rain and flooding, wind and downbursts, hail, tornadoes, and lightning. Those are just some of the hazards that come along with these storms. So the first one I'm going to talk about is flash flooding. Now, I personally think that this hazard gets overlooked by many, and this is actually the most deadly storm hazard. So it kills the most people behind a heat hazard. So slow-moving thunderstorms, any type of slow-moving thunderstorm, whether it be pop-up or supercell, is going to drop a lot of hail or a lot of rain in one spot. And these flash floods can pop up very quickly and be very strong with their currents. So they are deadly, they're destructive, and no, your vehicles are not safe. If you cannot see the bottom of that road, you should not be driving in it. we have the saying with the National Weather Service, turn around, don't drown. So again, flash floods kill many people from thunderstorms, and they are very quick. So if you get that flash flood alert, just don't risk it. The next one is going to be hail formation. So I talked a little bit about a convection cell earlier and about those updrafts and downdrafts in a thunderstorm. Well, hail actually gets formed within those updrafts and in thunderstorms. So as raindrops are sucked up higher into the cloud, if you'll remember, I said it's colder up there. Higher in the atmosphere is going to be colder. So the liquid drops that are on the bottom of this cloud are going to be pushed up by that updraft high into the cloud. And then they're gonna fall down when they're out of the updraft and get pulled back up and then fall down and pulled back up. And they kind of do that rotation inside a thunderstorm until the updraft is not strong enough to hold it up in the air anymore. And then it's gonna fall down in the form of a hail crystal that kind of has rings like an onion. So let me show you full screen. If you'll look on the side of your screen, you can see a cross section of a hailstone that actually has those layers. Now that is from it going up and down inside the thunderstorm over and over and accumulating liquid on the edge and then freezing once it gets higher into the sky. So in order for those hailstones to be very large, that thunderstorm needs to have a very, very strong updraft to keep it going. So I find hail pretty fascinating, the fact that it has done so many trips around this cloud before it came down, and it does range in size. So this video here is from a storm back in Texas in 2019. I'm gonna play this and I'll play it full screen. You can see just how large and crazy these hailstones can get with their damage or just how they act. So let me go full screen. All right, so you can see that there is some massive hailstones there falling into someone's pool. And not only can hail be hazardous when it's falling, you don't want to get hit by those stones, but there also can be accumulation of hail. We had a storm pass by a few shifts ago, so probably a little over a month ago, where I remember Portland, Maine was shoveling hail. So it accumulated on the ground as if it was snow. So hail can be pretty impressive, not only in its size, but also potentially in its accumulation. All right, so we have next what's called a downburst. So I have talked about updrafts. They are very important in thunderstorms. Now what a downburst is going to be this strong updraft pushing up. And you remember I said it was pulling up those particles, maybe creating hail. Well, this strong updraft is going to hold onto a precipitation core. So basically just a pot of precipitation being held in the sky. And once that precipitation core gets, let's say, too heavy, or maybe dry air is introduced into the thunderstorm, it's going to suck and fall down. It's going to basically drop everything it has all in one go. And so downbursts can be very, very dangerous. They can also form straight line winds coming out of them after they've dropped their pocket of rain and hail. So this is something that does endanger the whites. It is a threat or a hazard up here in the White Mountains. And we can see over here an example from Mount Washington. So this is our typical haze chart up here on Mount Washington. The way you would read it is the further out from the center of that circle, the higher the winds. So let me make this full screen for you. And now look at the haze chart. You can see that throughout the day, it was pretty close to the center of the circle. However, in that bottom right-hand side of that haze chart, you see one big spike. Now that is a 106 mile an hour spike of winds, when winds were sustained at, let's say, 56 to 66 miles an hour. So just imagine hiking and only having about 50 to 60 miles an hour winds, and then having that giant burst of precipitation, wind, hail. That's probably gonna knock you on your butt if you're out there hiking. So downbursts are definitely something to be aware of, and they can be pretty damaging, not only above tree line, but let's say if you're down in the valley and you have that downburst come down, it could knock out trees, it could knock out power lines. And again, sometimes downbursts get confused with tornadoes, but this is a straight line wind. So here is a video I'll make it full screen. Pay attention to the precipitation and to the water underneath the precipitation. And you can tell me if you see that downburst. All right, so hopefully you were able to see that drop of precipitation and kind of that rippling out of the water as those straight line winds come out from it. So this is definitely something to pay attention to. And yes, I see somebody commenting airports. Yes, airports. This is super, super important for planes flying in. And let's say they're flying and then they get hit by a downburst. So definitely something to be paying attention to when thunderstorms are in the area. So we also have tornadoes. I said I would get into this in a little bit. So this here is the same exact radar image that I used when I was describing supercells. Now I'm going to describe it in a little bit more detail. So this is what we like to call a hook echo. It kind of looks like a little hook. So supercells are going to be these giant rotating thunderstorms. And this here is showing that rotation. You can actually kind of see the spiral to the radar. So that is going to be a rotating thunderstorm. And within it, it can have those rotating columns of air that can turn into these tornadoes. And tornadoes are going to be a funnel cloud that actually touches the ground. So we have funnel clouds, you can have water spouts, you can have tornadoes. Tornadoes must be touching the ground. And these, again, are mostly produced out of our supercell thunderstorms because of that rotation and because inside of a supercell thunderstorm, their updraft is actually rotating. That's one of the requirements to become a supercell, is to have that rotating updraft. So these are going to be super dangerous. Tornadoes can range in size, they can range in their damage, but overall, tornadoes are going to be a very big hazard. Now, lastly, we are going to get into lightning, and that is where my talk ends, and I hand it over to John Jensenius, who is going to be our expert on lightning safety and tell us all about the hazard of that. So go ahead and take it away, John.
Well, thank you, Nicole, and thank you all for joining. First of all, I want to thank Brian and the Mount Washington Observatory for hosting this program. I really appreciate it. Lightning is my favorite part of a thunderstorm, but I'm also very concerned about people who could be killed or injured by lightning. So I've been working on lightning safety for about the past 20 years, initially with a National Weather Service in Gray, and also nationally with the National Weather Service, and then also now with the National Lightning Safety Council. So I want to get started. First of all, I'm going to be sharing my screen most of the time here. So if you'll give me a second to start sharing my screen, I will go ahead and get started. So first of all, every year in the United States, there are about 20 million cloud-to-ground flashes of lightning. And most importantly, each one of those is a potential killer. If we look at the United States and the distribution of lightning flashes across the United States, you can see that areas of Florida, along the Gulf Coast, and the Mississippi Valley have the greatest tendency of or densities of lightning. However, when you consider the size of the state and the amount of lightning, Texas actually has more lightning than any other state in the country. And in fact, it has more than twice as much lightning as the state of Florida. So the 32% of you that answered Texas, you're absolutely correct. So what is lightning? Well, I like to think of lightning as a giant spark of electricity that's either in the atmosphere or between the atmosphere and the ground. In terms of power, lightning is about 300 million volts, can be stronger, about 20,000 amps. If you compare that to household current is usually 120 amps or 240 amps, depending on the circuit, and usually 15 to 20 amps. So obviously much more powerful than your household current. Nicole did a great job of talking about thunderstorms, so I'm going to pick off somewhat about where she left off in terms of the electrification of the cloud, thunderstorm cloud, and lightning. First of all, in that updraft, we have various types of precipitation. Nicole talked about the rising air in the thunderstorm. You have the very small cloud droplets. You also have several different combinations of ice in the cloud. What I've shown as snowflakes, or what we call ice crystals, they're actually very small. I showed them rather large compared to the other thing, which is called graupel, which is like a pellet of snow. The ice crystals are light, small, and carried upward by that updraft in the thunderstorm. The graupel tends to fall or be suspended in the thunderstorm cloud. So our thunderstorm cloud looks something like that, where those positive charges, the ice crystals are taking the positive charges to the top of the cloud. The graupel is creating a large pool of negative charge in the central part of the storm. It's almost like a great big battery in the atmosphere. And that battery is going to supply the energy to produce the lightning. Now that negative charge in the central part of the storm, central and lower part of the storm, also induces a positive charge on the ground underneath it. Out away from the center of the storm, you may have a bit of a negative charge under the anvil of the storm, which is positively charged. But right under the storm, the pool of negative charge induces a positive charge. And if you're outside, you may become positively charged. It's okay to be a positive person, but not good to be positively charged. Might look something like that. Obviously, these two are in a great amount of danger at this point. Lightning did strike shortly after the picture. There was one person killed. Neither one of these two were killed, although one of them was injured. So if we look at our thunderstorm cloud, there's various types of lightning, intra-cloud lightning between the positive and negative charges in the cloud, negative cloud to ground lightning flashes between the pool of negative charge and the positively charged ground underneath, and positively cloud to ground flashes which strike out around the storm, which often catch people by surprise. Today I'm going to be talking mainly about the negative cloud to ground flashes that you see on the screen right now. So just a picture of some of those flashes. They can come either out the side of the storm from that pool of negative charge, or they can come from underneath the storm, which is where most of the flashes occur. So what happens is once the charge builds up enough, you start getting negative charge that starts flowing from the negative pool toward the ground. It emerges from the base of the cloud as something we call a step leader. Actually steps its way to the ground. It's going down blindly. It's not attracted to anything, and it's just looking for a connection on the ground. As it approaches the ground, opposite charges reach up to meet it, and eventually you get a connection. Once you get that connection, then the whole process can actually start, where you start to get the lightning flash. So the lightning flash starts at the connection, and it just simply drains that whole channel of negative charge from the lightning. And as it does so, as it drains that charge, it illuminates the channel. So although the charge is going down, the illumination of the lightning channel goes upward into the cloud. If there's additional charge available, something called a dart leader will come down that ionized channel left by the initial return stroke. And with every dart leader, once it reaches the ground, you get another return stroke. So, and that causes the lightning to flicker. So if you're seeing lightning flicker, those are additional dart leaders and return strokes. So in slow motion, if we put it all together, it starts as a step leader. As it approaches the ground, you get streamers that rise up to meet it. You get contact, an initial return stroke, which is branched, then followed by dart leaders and subsequent return strokes. All of this happens in a fraction of a second, looks something like that. So here's a video. This is of a step leader coming down, somewhat overexposed. Once one of the channels reaches the ground, you do get the actual return stroke. And I can actually step through this frame by frame. And you can take a look. It's just simply a race to the ground. All of them are going down blindly. And then one reaches the ground and you get the full return stroke. All of what you just saw there happened in about 1/100th of a second. So very, very fast. So the initial step leader and the return stroke are branched. Subsequent dart leaders and return strokes are not usually branched. And then there's something called continuing current, which occurs if there's a continuous flow of electricity rather than the dart leaders. Flashes that contain dart leaders and return strokes, as I said, tend to flicker. Flashes that contain continuing current tend to pulsate, and some flashes are hybrids and contain both. This is another video, same thing. All this happens in 1/50th of a second. It's 2-liter tips racing to the ground. The first one that gets there discharges the channel. And in this case, there's continuing current. You can see that discharge pulsating a little bit. So as far as safety information, the one thing that you need to know is there's simply no safe place outside when a thunderstorm is in the area. And by in the area, if you hear a thunderstorm, there's a thunderstorm in your area. You need to get inside a substantial building or a hard-topped vehicle if you want to be safe. In terms of what we mean by a safe shelter, the substantial building needs to have wiring and plumbing throughout. That should tell you something. If it's going to have wiring and plumbing, what's going to happen is the lightning is going to follow that wiring and plumbing to the ground, which should tell you you don't want to be in any way connected to the wiring or plumbing, because if you are connected to anything that plugs into the wall, you're in danger of getting struck by lightning. Hardtop vehicles are also safe. It's not because of the rubber tires. The rubber tires do nothing to protect you. It's the metal shell of the car that protects you. In fact, cars are struck every year. Usually the metal tires are blown out, the electrical system is damaged, and typically the cars stop after they've been struck by lightning. Small open shelters are simply not safe during thunderstorms. You don't want to be there. So what should you do if you can't get to a substantial building or a hardtop vehicle? That's a question I'm asked all the time. And my answer is, you need to figure out what you've done wrong so you don't get caught in that situation again, because really there isn't anything you can do that would prevent you from getting struck by lightning if that step leader is coming down right above you. There are things that we do recommend that slightly reduce your risk outdoors. You want to avoid open areas. You want to avoid tall or isolated objects. You want to avoid contact with metal fences or wires. And we recommend you run as fast as you can to get to a safer location. Why? Well, one reason is that a typical thunderstorm, at least the danger from it, lasts an hour or longer. And if you can get to that safe place in a half an hour, you've already cut your risk in half. You certainly don't want to lie on the ground. Lightning tends to spread out along the ground surface, and if you're lying on the ground, you're more vulnerable to the lightning strike. The one problem is we provide that information, but lightning doesn't follow rules. That's a picture of the space shuttle. You'll notice this pointy thing up top above the space shuttle. That's to intercept the lightning. Lightning didn't even know it was there. It simply went around and struck the base of the space shuttle. We also say that to avoid the tall trees, and that's true. You don't want to be in an area of tall trees or standing next to a tall tree. But look, there's a tall tree there, there's a big tree there, there's a big tree over there. What tree got struck? It was a smaller tree. I'm not saying that it wasn't as tall, but if you were in the forest, you might have thought, well, there's not really a chance this tree is going to be struck. But again, lightning doesn't follow the rules. We keep track of lightning fatalities so that we can learn from them. That happens to be lightning fatalities since 2010. About 270 people have been struck and killed by lightning since 2010 in the United States. If we look at fatalities by state, of course, areas that are populated and have a lot of lightning tend to have a lot of lightning fatalities in just the raw numbers. But if we look at a population weighted, so the individual's chance of being struck by lightning, you'll see that there are other areas of the country, areas where people tend to be outside more. So it's not just the lightning or the population, but it's vulnerability. Whether people are outside and vulnerable to being struck that contributes to lightning fatalities. The way people are struck, most people think of direct fatalities. It doesn't happen that often, certainly very dangerous, but people do survive direct strikes. Why? Well, the entire amount of electricity doesn't really go through them. You can think of a bucket of water and a straw and trying to very quickly pour a bucket of water through a straw. Some of it's going to go through the straw, but most of it's going to go around. And that's what happens with lightning. Most of it goes around. Although that little bit that goes through the straw is certainly enough to either injure or kill you. The other type is a side flash or side splash. People like to take shelter under trees to keep from getting wet. That is very dangerous. As you can see, a person took shelter under this tree. He was standing right there. Lightning came down the tree and jumped to the person. Unfortunately, he was killed in that particular incident. Most people are struck by ground current. As lightning is spreading out along the ground, literally can go up one leg and down the other through the cardiovascular or nervous system, stop the heart. And that's how most people we think are killed or injured by lightning, is through the ground current. An example of that on a golf course, how lightning spread out on a golf green. And ground current is responsible for killing many animals throughout the United States during the course of a year. Conduction, I already mentioned that. You don't want to be connected with wires in any way, whether they be outside or inside. And then finally, an example of that. And finally, what we call streamers is a case where you may not be in contact with a direct lightning strike, but those streamers that I mentioned that are reaching up to meet the step leader, there are more than one, but all of them discharge at the same time. And if you're caught in one of those, you could be killed or injured too. And just a picture showing an example in the background, you see a couple of streamers coming off of trees here, possibly looking toward this part of the step leader as it was coming down. If somebody is struck, call for help right away and begin CPR if necessary. We track lightning fatalities across the United States so we can learn what we can. Most importantly, what we're trying to learn is what people are involved in that are putting them at risk. About 80% of the fatalities are men. There are some reasons for that. Some of you may have your own ideas on that. About 2/3 of the fatalities, the people were involved in leisure activities before being struck. When we look at those leisure activities, water-related activities, sports, camping, and riding are all right there as far as activities that put a lot of people at risk. And if we break up the water-related activities, fishing, it takes a large chunk of that. And those are all activities that a lot of men are involved with, and which is one of the reasons that men contribute to 80% of the lightning fatalities. So looking at the deadly dozen, and I'll just take the top 6 here: fishing, beach activities, camping, farming, ranching, bikes, and boating. Again, these are all activities that may require extra time to safety, and that extra time is what you may need to plan for so that you can be safe. If you're going to be out some distance from safety, make sure you have a plan so you can get to a safe place quickly if a thunderstorm develops. So why are people struck by lightning? Well, perhaps they don't understand the dangers of lightning, or they may choose to just ignore those dangers. They may not realize that a storm is approaching, especially, for example, if you're on the beach, you're looking to the east, and the sounds of the surf may hide some of the thunder that's coming. You may not know a storm is coming. They may just simply wait too long to head to safety, or perhaps they just can't get to safety before this storm arrives. All of it comes into proper planning. Plan ahead, know where you're going to go for safety, how long it will take you to get there, listen to the forecast, consider canceling or postponing an activity if thunderstorms are forecast, monitor the weather, keep an eye on the sky, and get to a safe place quickly if you start to see threatening skies or you hear thunder. And we recommend waiting 30 minutes after the last thunder before returning outside. So that's a quick look at what I have here. I wanted to very quickly show a video. This is kind of I consider your final exam, I want all of you out there to take a look at this and think in your minds what lightning is going to strike based on the information that you already know. So if you've all thought about that, I'm going to go ahead and play the video. And I'll stop it there. For those of you that said it looks like lightning is going to strike that tall tree, I am going to give you partial credit. Okay, why not full credit? Well, let's talk about some other things. For those of you that said it was going to strike the building over here, let's watch this light. You'll see the light explode. So lightning struck the tree and it struck the light. For those of you that said the metal fence, let's look down here. And you can see lightning struck the fence as well. And for those of you, and I doubt that anybody did, say it's going to strike over here, you can see a puff of smoke. Lightning doesn't strike a single spot, it strikes an area. It spreads out when it strikes. So with that, I'm going to go ahead and stop sharing my screen. Thank you all for listening.
Wow, thank you so much, John. That was obviously any one of these smaller topics could easily spend an entire evening discussing, but really appreciate you, John, taking the time to discuss this, and Nicole as well. We have lots of great questions that have been popping up. Thanks to everyone who's been putting questions on the Q&A button at the lower bottom of your screen there on your Zoom screen. So please add some more questions. We're going to try and get through as many as we can quickly. So for Nicole and John, we'll just say we'll stick to some overly simplified responses if we can, so that way we can make sure we can get a lot of folks in. Started with a really great question from Walter. He said, I noticed that in Quebec, thunderstorm warnings are posted down to their southern border, but often no warnings are posted in northern Vermont, where the storm should be theoretically impacting as well. Is there a difference in storm posting standards in Canada versus the US? And John, I guess as a former National Weather Service employee, I don't know if you want to very simply try and explain that one, because I don't know Canadian weather standards.
No, and very short answer. I don't know the standards in Canada either. So I'm really not sure. What I can say is that each of us, we'd be watching our own radars and making our own decisions on that. But I don't know if theirs are any different.
Yes, certainly National Weather Service does have its own area of responsibility. And once it gets out of the US, well, I'm sure, well, at least I hope there's some communication there. So moving quickly, I think we'll go right back to you, John. The question that comes up a lot, what is heat lightning, or have you heard of heat lightning, and why is there sometimes lightning with no thunder? I thought thunder was a result of lightning, asks Joanne.
Yeah, well, that's a very good question. Heat lightning is just simply lightning from a thunderstorm that's so far away that you can't hear the thunder. It depends a bit on atmospheric conditions and surrounding noise, but typically we say that you can hear thunder about 10 miles with normal noise around you. Sometimes you can hear it farther, but if you're not hearing the thunder and there's not a lot of noise around you, it means the thunderstorm is distant and you're safe. But you can see the light from a thunderstorm, particularly if it's bouncing off the top of a cloud, which is often what's happening with heat lightning.
Yeah, that's great. Nicole, question for you perhaps from Tracy. How do ice crystals form in thunderclouds? So going right back to our thunderstorm development.
Yeah, so I mentioned that there are the strong updrafts that are going to be bringing the particles from a fair weather cumulus cloud to the towering cumulus cloud up and into the high atmosphere. So you're going to get those ice crystals start to form once you hit the temperature of freezing in the atmosphere. So as those liquid particles go high in the sky, you're going to have some freezing, and that's how we get our ice crystals that possibly turn into hail.
And sticking with you, Nicole, another question that it looked like Stacy was looking for a reminder. What is the geological forcing, that feature that causes air to rise, called again?
Orographic lift.
Yeah, so orographic, that comes up quite a bit, and a good reason why Mount Washington gets a lot of upslope snow showers too. The mountains like to wring out the moisture, that's for sure. Oh, another good question actually from Tracy. These terms come up quite a bit. The difference between a downburst and wind shear. I don't know, Nicole, if you want to capture that one real quick.
Sure. So a downburst is going to be that that burst of air that comes down and out of a thunderstorm. It's going to be your straight line winds that kind of get dropped and out of a storm. Wind shear, there are different types of wind shear. There's going to be directional wind shear, so that means that at two different levels of the atmosphere, you're going to have winds going in different directions. And there's also going to be the wind shear of speed. So maybe you have very slow air going at like the surface and it's faster up above. So there's two different types of wind shear. Downbursts are going to be just straight line winds coming out of a thunderstorm, and wind shear can happen at different elevations in the cloud.
Oh, that's great. Thank you. Oh, here's a great question from Marie. John, maybe you can take this one. Is capturing the energy from lightning as an alternative energy source being researched, or has it been researched? Do you have any connections on that one?
Well, I don't have any connections, but to answer that question, lightning is extremely powerful, but it also occurs instantaneous, so it doesn't last very long. There was an estimate at one time, and I think it's still valid, that a typical lightning flash can light a 100-watt light bulb for about 3 months. Now, light bulbs have changed since that estimate was made, so with the newer light bulbs, I think it could illuminate it for about a year. So you've got 20,000 100-watt light bulbs for a whole year. But if you consider 300 million people, that means that everyone, if we took all the lightning and captured all the lightning in the United States, we'd still only be illuminating every person's light bulb for only about a month. So there really isn't as much energy there as people think when you start spreading it out. It's so very concentrated. But the other problem is you would have a lot of difficulty capturing the randomness of that lightning, even if you could capture it.
Yeah, so for anyone attending tonight, there's the Nobel Prize project right there, if you can figure out how to capture lightning in a bottle. A couple questions have come together here, John, asking about some scenarios about, say you're, one anonymous person asked a question, as did Bryant, who wrote in via email, asking about the best way to ride out storms, to stay safe when you're out in open water and shelter is difficult to find, either in a sailboat or on a canoe trip. Any thoughts around that?
Well, yes, I do have some thoughts. First of all, definitely put on your life jacket, because if you are struck by lightning, it can cause your muscles to contract, and you're a lot easier to find in the water if you have a life jacket on, and it will keep your head up, hopefully keep your head above water, or at least long enough so you can be rescued. If you have a cabin, you're better off in the cabin. If it's an open boat, there really isn't anything that's going to protect you. So the main thing is it's a situation where you just simply don't want to be there, a situation where you have to figure out next time, you figure out what you can do so you don't get in that situation. But by all means, put that life jacket on, and if you have a cabin, get inside. If it's a metal cabin, it's like a car and you'll be safe. That's
great, thank you. And then we'll have to wrap it here for the last sort of question. A few different questions have come up around the ideas of what do you do when you're out in the mountains above tree line? How frequently are the mountains seeing lightning strikes? Nicole, have you been on the summit for lightning strikes?
Oh yeah, I've been on the summit for a few direct strikes to either the summit itself or the building, which is pretty scary. For somebody that absolutely loves thunderstorm and lightning, it's terrifying for me. So I wouldn't want anybody to be caught out in those conditions. As I said, the thunderstorms can spark those storms themselves. So when we put our threat of thunderstorms in our forecasts up here, it's definitely something to keep in mind when you're above tree line or even below tree line.
And I'll say
Awesome.
That's where checking out the forecast, and don't go if thunderstorms are forecast.
Yeah, so that's a great pitch right there for Mount Washington Observatory's Higher Summits Outlook, and obviously National Weather Service forecast products as well. So stay tuned to all those. We are at just past 8 o'clock here, so I want to be respectful of everyone's time, especially John and Nicole. Thank you both so much for joining us this evening. For any questions we didn't get to tonight, especially on Facebook or via email, we'll try our best to get to those after the fact. If you enjoyed tonight's free program, by all means, we encourage you to donate and support the Mount Washington Observatory. Join as a member, go to mountwashington.org to support this nonprofit organization. We can do programs because you support them. So we appreciate you following up if you enjoyed this program and programs like it. Have to say, if you enjoyed tonight, it gets even better in a couple weeks here as we continue to chug along. August 25th at 7 p.m., we will be talking about the legacy of Hurricane Irene. In fact, it'll be a little different, a panel discussion in which we're going to have Nicole's counterpart on the mountain there, Ryan Knapp, who will talk about the meteorology of Hurricane Irene and the lasting legacy. Mary Stampone, UNH professor and New Hampshire State climatologist, will be talking about the climatological context and impact of Hurricane Irene. And we'll also have David Hollinger, who's the director of the USDA's Northeast Climate Hub down in Durham, New Hampshire as well, talking about the ecological and economic impacts of tropical systems. So please join us there. You can register at mountwashington.org/SITM. I think that's all we have for you tonight. So thank you again so much for joining. We appreciate you joining us this nice hot evening in Northern New England, and we'll see you again real soon. Take care, everybody.
Bye.